is to have.
Hello, welcome back. How are the final projects going? I realized we have, what, another week left?
Oops.
This and next. So next week, I think it's business as usual. I mean, this week, next week, business as usual. The week after is ICSI? Is that right? So then I'm gone, no class. And then presumably presentations like the week after that. Is that right? So like we have
4 weeks.
3 weeks? Is that right?
Yikes.
Did I do the math? I'm not sure. I'm asking. Is that I can't believe how quickly somehow it feels like the semester went by very quickly. We just have
This class for CMU.
probably
Schedule.
as on or off.
There's a structure on it.
Yeah, so that means So
There's
then
1 day less.
yeah. So then we got to get going. There's so much still I want to cover and teach you. I feel like I'm running out of time. Okay, there's a few, so please page back the projects into your working memory, and maybe start working on them.
Is that the last week of the semester after exam? The week after exam?
Presentations.
Yes.
What did we say in the thing?
Yeah.
I mean, so we could push it back probably more if we need to. Do we need to? Okay, so
Not a bad idea.
yeah. So, when are the final reports due? We could push the presentations out more if we need.
I don't think we are told.
Are you 29? Okay. Oh, no, sorry, that's not our.
Did I say anything about when the final
No,
reports are
I
due?
didn't.
So there's one hard, I mean, we're pretty flexible here, but there's one hard deadline, which is CMU grading. We cannot push, plus I need some time to read them and give some feedback. So like, we're hard constrained by CMU grading deadlines. And working backwards from that, we need time to review and whatnot. Great. But okay, I'll look at dates to see if there's any room for flexibility there, and I'll let everyone know. It's hot. Okay, so today I want to tie some loose ends from last time, hopefully. And let me start with this business of standardized coefficients. So here's a simple example. I don't know that I have a deck today. I have more notebooks and things like this to look at instead of a deck. Here's a concrete example. We're trying to predict monthly earnings or model explain monthly earnings as a function of a number of things. IQ, what's knowledge, measure of knowledge of their job, years of education, years of experience, and years at the current job or tenure. Okay, so that's kind of the setup, right? There's some data set for this. If you look at this model, for example, you could ask questions around some of these variables of interest. In this case, like, how much is experience on the job worth versus education worth? Very, common standard question that you might want to ask. Okay? So if you look at this model, what would you conclude there? Like, what's the relative value of one additional year of education compared to, say, an additional year of experience? How much is a degree worth? Should you get a PhD, or are you better off just going to industry right after undergrad? Not a trick question. I'm asking you to interpret the model that's on the screen.
Go for PhD
Explain.
because it has a higher estimate.
Explain.
So that basically means that the correlation between like the slope associated with years education is higher. So that means a unit increase in your years of education leads to a 47 unit increase in whatever the Y value was.
Yeah, monthly wages in some unit. Okay, so controlling for all those things, one extra year of education gives you about 50 more, I don't know, dollars of monthly earnings. One extra year of experience gets you about $12 of extra earnings. Is that fair? That's the data, right? No tricks. I'm sensing some skepticism. On the one hand, I'm excited that you've become skeptics, which is what I've been trying to, instill in you this whole time. On the other hand, we just started, so I'm not tricking you just yet. We have time for tricks in a minute. Marco.
Just doesn't seem right. I mean, earning on out like for 1 year of education to earn 4 times as much in comparison to years of experience.
Yeah, so controlling for everything, the ratio differential is 4-to-1, right? 4-to-1 in favor of education. Interesting. I mean, on this data set, it is what it is. It comes from somewhere. Okay. Okay. So, right, if you look at the diagnostics for this model, they all look very good. So, residuals versus fitted looks random, etc. Like all of these ones look good. So nothing to complain about there too much. These are the distributions we talked about. Okay, so now back to the question, like education versus experience. Here's a thing that we haven't talked about, right? So what is actually the range of these two variables? Okay? So education ranges from 9, everybody has at least 9 years of education. I guess that's what, elementary school? Middle school? Middle school. Is that right? No.
Yeah, ninth grade is the end, and then 12th grade is high school.
Yes. Right. So you have at least middle school and at most, I don't know what this is. This is the equivalent of a PhD? College? I don't know what that means. 18 years of experience.
So 12 is high school, so then 4 would be for bachelor's, so that's 16.
16.
So it's master's.
Masters. Okay, so no PhDs. So it goes from elementary school at the very least to masters at most. That's the range. Okay. If you look at experience, the range is quite different actually. Right? Experience ranges from 1 year, I guess, that's the lowest, to 23 years on the sample. So very different range. Okay, so what this means is that possibly these things are not quite as directly comparable as you might think if you just look at them directly without any additional transformation. So the trick is to transform these variables so they're both on the same scale, which makes interpretation more natural, oftentimes. Right? For these variables and other variables, especially variables that are measured in different units, right, that are fundamentally not directly comparable, you can still compare them if you scale them in a meaningful way. The standard way to scale them is to, what is this called? A Z transform or something? Mean 0, standard deviation 1. What is this called?
Nominalizations.
Z scale? Okay. So that's a standard way of scaling these variables because the interpretation of the regression coefficients then is done in terms of standard deviation increases in those variables compared to unit increases in those variables, which is actually quite meaningful. So in R, you would do this with scale built-in function that transforms this. So if you look, years of experience, untransformed, it's a normal distribution with a mean around 10. That was the data that we had. Years experience scaled is still a normal distribution that does not change. But now the mean is 0 and the standard deviation is 1. Okay? So if we do this, standard deviation, just to confirm, is 1 by construction. That's what the scaling thing does. So not a trick. So now we can model the scaled versions of these variables instead of the original and untransformed ones. Okay? So if we look at this model, things are looking very different. What's the interpretation now?
The ratio changed from 4:1 to 2:1.
Ratio changed from 4:1 in favor of education to 2:1 in favor of education. That's quite a drastic change. Yeah, Marco.
So for every 1 unit of increase in standard deviation.
For every standard deviation increase
Yeah.
in education. So if education goes up by 1 standard deviation, whatever that value is, you get about about $100 more monthly wages. If experience goes up by a standard deviation, you get about a $50 more a month in wages.
Isn't it still increase in years of 1 year of experience leads to $51 as opposed to standard deviation number of years?
So both of these are true at the same time. On the original scale, on the original scale, 1 year of experience is about $10 more in wages. One year of experience, but 1 standard deviation in experience is more than 1 year. I don't know if I have that computed here. So it is whatever it is. Do we have it? Do I have it? Do I have it?
Oh, so the results don't technically change because they're with respect to each other's standard deviations. Is that right?
I don't have it. Yes. So 1 standard deviation in, oh yeah. No, standard deviation is, wait. I don't have the standard deviation of the original experience here, so I can't tell you what the number is. Of course, the transformed one is 1 by construction. But yes, in units of standard deviation, which is however many years, maybe about 5, I guess. But that's a more meaningful unit to reason about.
Has to be 5, right? From the previous value.
You can expect that, yeah. But it's a more meaningful unit to reason about because the range of these 2 variables are different. Right? So, 1 year of education is harder to get than 1 year of extra of experience.
Just because in the data set you had different ranges of years.
Yeah. So you reason about normalized regression coefficients, which are the ones you estimate on the scaled transformed variables. Okay, so this is often a very useful trick. It's also a useful trick because now you can reason about the differential effect of education versus, say, IQ, which you cannot otherwise because they're like different units of measurement.
They're still different units. 1 standard deviation of education years is different from 1 standard deviation of experiences.
Yes, but you, in terms of shifting the distribution, they're the same. It's standard deviation shifts in the distribution. So that's a natural way to reason about the coefficients. Okay, so this is often a very useful trick. And I think we've seen this in some of the papers we read before, but we didn't really pause to reflect on it. So hopefully you will remember this one. Yes? Okay, here's another one that maybe we've seen a bit. I don't know if we talked about this in lecture before, but here are one response variable y and two predictors x1 and x2. Notice how y is exactly x1 plus x2 in this example. And otherwise x1 and x2 are identical. Okay. So if I estimate this model, what will happen?
You get estimates as 1 and 1.
Good guess.
That's solution.
Say again.
Infinite. That's solution.
Infinite perfect solution. That's a better guess. Right? It could be anything. It could be x1 plus x2. It could be twice x1 without any x2. Could be twice x2 without any x1. Could be three x1s minus an x2. Could be all of these and many, many more that are all equally good. Right? Which means what? Which means you can actually estimate the coefficients. Right? You just don't have enough information to estimate the coefficients more precisely. They could be anything. In fact, if you try to do this, R will complain that it's illegal, right? It simply cannot do this. Okay? So maybe that's an unrealistic expectation. It's never this, you don't usually have identical variables in a model. So let's yeah, so here, look. It estimated 2 times x1 and it crashed on x2, right? Because it couldn't figure out what to do with it. So fine, let's add some noise to this so they're not identical, so we can get R to estimate these coefficients. So I have just ever so slightly perturbed one of the variables here. They're still almost the same, just added a bit of noise, so R won't complain. Okay. Just change them a little bit. So now, what would you expect?
Really the same.
Okay, two very different opinions. There'll be only one solution versus still the same problem as before. Why?
Because the noise is constant. So that's just a constant deviation.
Not really. Look, like the 6.5 is 615. It's not
Oh,
quite. I mean, there's some noise. Any guesses? Any other guesses? Marco, why?
Well, I mean, maybe I'm missing some, these are coefficients, right?
So these are the original variables. You're estimating the regression coefficients, right? Beta 1 times x1 plus beta 2 times x2 plus some error term. You're estimating the beta 1s and beta 2s. Like, how confidently can you do that?
you should have one solution because there are like the noise term. Technically, you're gonna estimate only the beta 1 and beta 2 with the noise term.
But has our problem from before fundamentally gone away or not? Can I specify this as x1 plus x2, so meaning beta 1 is 1, beta 2 is 1, or two times x1 without any x2, or any of the other combinations of this? Could I not do that still?
Sure. So it's still many.
So it's still the same problem, right? I've cheated a bit so R doesn't complain, but I haven't actually solved the problem in any way. It's still all the same problem from before, right? So if you look at, yes, so now R will estimate something. In this case, it estimates 2 times x1 plus about 0 times x2. So the way you read the second one is 5.4 times 10 to the minus 15. So that's basically 0. Okay. And I think it does something silly like it did with categorical variables before. It just goes alphabetically. So like it prefers x1 here just because it came first or something. Or it's alphabetically before the other one. There's no reason why this is the good solution here. You could have specified this in the other way, just the same. So I guess in this case, x1 is maybe like 2 times x1 is closer, there's less error. So maybe this is not the best example to illustrate my point, but I think you get the idea. It's fundamentally the same problem we had before. There are still, I could have perturbed both of these a little bit instead of just one. Okay, so this is called multicollinearity. When you have highly correlated variables in a regression like this, then you cannot reliably estimate these regression coefficients because there could be infinitely many. If the two variables are perfectly correlated, which was the artificial example we started with, there could literally be infinitely many equally good solutions to this. Okay, so that's fundamentally the same problem. We haven't quite solved that. Like usually you want to diagnose this because because your coefficient estimates are unreliable and usually your standard errors are very high. I don't know why they're low here. I don't quite understand this. So let's ignore my confusion for now. The point stands that you cannot reliably estimate these coefficients if you have collinear variables, meaning highly correlated variables in your model. Okay, so what do you do?
Remove the collinearity.
How? You could do that. Yeah, you could reduce the dimensionality of your input with something like factor analysis, like we did with the survey thing. That's a lot of work. You could do that. That's fine. It's a good solution. Something else? Just drop some. So, highly correlated variables means they carry the same information, right? So if they carry the same information, you don't need all the clones. You just need one of them, right? Because they all carry the same information by definition. That's why they're highly correlated. And that's what it means to be highly correlated. So you just drop one, right? You drop one. How do you diagnose which ones to drop? You could study, pairwise correlations between variables. You could do that, look at some table of these pairwise correlations. There's also a shortcut. It's called the variance inflation factor. You could look at how this is computed. It gives you a measure of collinearity between variables in a regression. And there's some magic thresholds that you can apply to decide which of these things are collinear and to remove some of them from your model. So once you do that, once you remove the I guess for every cluster of highly correlated variables, you remove all but one of them is usually the practice. Right? Because one is sufficient to capture that information that they all share. Okay. When you do that, then you will get much more reliable coefficient estimates, much smaller standard errors for them, usually. Okay, that makes sense? So high level bit is you should diagnose usually multicollinearity in a regression model that you're estimating because your estimates are unreliable if there is collinearity. Okay. So now trick question. Do you care about multicollinearity in your explanatory variables, or do you care about collinearity in your control variables, or both? By explanatory variables and control variables, I mean explanatory variables are the things you explicitly test hypotheses about. They're the things you care about in your study. Control variables are all the things you include in your model to control for covariates. Remember the Google AI paper, they included a control for, I don't know, hours of programming experience or something like this, right? Because they expected that performance on their task varies with programming experience. That was a control. That was not the interesting explanatory variable. The interesting explanatory variable for them was which condition you were in, whether or not you used AI to complete a task. So that would be an explanatory variable. Years of experience or whatever, hours of experience would be a control variable. So the things you don't so much care about.
Both,
Both. Argue?
because I mean, it's part of the same equation.
Yes.
So you want to test for that and non-possible stuff, because otherwise the same issue will happen. Like the model does not know what is control, what is
Correct. The model does not know what is control and what is explanatory. Only you know, right? So that means if there is multicollinearity among controls, the estimated coefficients for those variables will be unreliable, right? Same logic as before. Do you actually care? The answer is no, because you don't actually care about the controls to begin with. You're not testing hypotheses about the controls. You're including the controls to separate out variance that can be attributable to them from the main effect you're testing hypotheses about. Whether the estimated coefficients for the controls are or aren't reliable, who cares? Because you don't test hypotheses about the controls anyway. There's no harm if you remove them, by all means. You're welcome to. But if you actually think about what you're doing, there's also no need to remove them.
In the discussion we were doing before this, there was the case where the estimate was 4:1 in favor of education.
Yeah.
And when we scaled, there was 2:1.
Yeah.
Did we say that's a problem? Or is that not a problem? That the estimates change, right? With scaling.
The estimates change because the scale also changes, right? In the original one, we were talking about one unit, literally one absolute unit, meaning year, on the scale of possible years, ranging from, in terms of education from 9 to 18. And
but saying that one standard deviation of education years is comparable to one standard deviation of, or as like is the unit to compare against one standard deviation of experience. That's wrong, right? Like year is year. So in that year you could have done education or experience. But after scaling, the result you get is saying technically that, oh, it takes 3 years of education to be equivalent to 5 years of experience.
The only thing you're doing is you're considering the actual range.
But I'm trying to understand why is that better?
Um, it's better because um, Fahrenheit versus Celsius, for example.
But that is not the case here. Both of them are years.
It's better for the same reason, right? They're measured on different scales. So if experience goes from 1 to 20 some years, one additional year of experience is worth relatively little because it's 1 year of experience out of 25 years of experience. It's easy to get an additional year of experience because the range is so wide. Because education is much more compressed, getting an additional year of education is actually qualitatively different because it moves you much more on the distribution than it does a year of experience.
So maybe something that would be interesting to see like the upper half of salary per month, like monthly wages for, somebody who has a bunch of years of experience, but no education versus somebody with a bunch of education, no experience.
Yeah, this kind of
It's like informs.
boundary conditions or something like this. So this kind of analysis is always super interesting. You should always do this kind of inspection of your data, right? To observe these boundary behaviors. So good intuition. How is your scale question related to this multicollinearity business, or just kind of lingering from before? Okay, no problem. Any more on this? So two topics so far. One is scaling, which can help with comparing coefficients across, especially things that are measured in different units, but also things that are measured on different scales, even with the same unit. The second was this business of collinearity, how it impacts your estimated coefficients and what you should do to deal with it. Good so far? Okay, so then there was an interesting, let's look at an example. Oops. I really liked Shrey trying to teach us a bit about this mixed effects regression business last time. So let me pick this up a bit. Okay, so this is, by the way, this is a one-shot thing that Claude produced, surprisingly good. I gave it, 2-3 sentences of a prompt for a tutorial-like thing I would like, and it produced this thing, which I agree with almost entirely. So it's, very, very good. The scenario is the following. You have built some tool that you hypothesize reduces the number of bugs developers make when writing code. You recruit 30 people for a user study. Each participant completes 5 coding tasks, some with the tool, some without. Okay? And you count the number of bugs they produce in each of these conditions. Okay, so then the first thing you could do to analyze this data is run some standard regression model on this, right? So bugs here. Where does review? Oh, yeah. So I guess what does the static analysis tool have to do with the code review example? So this is Claude being weird. Forget about the previous example. So scenario is, does code review time predict the number of defects found? Like if you review code more intensively, do you find more bugs? That's the empirical question for your study. And you have, so this is a simulated data. You have 60 people in your sample. Is that right? And each of these review sessions take between 10 and 90 minutes, normal distribution. And I'm even specifying what the shape of this relationship looks like. So each additional minute of review time gives you 0.08 for bugs, plus some noise with with a normal distribution. Okay. Okay. So that's the data. Then you fit a simple linear model. You're trying to model defects as a function of review time, right? This is maybe the most intuitive thing you could do. Okay, so you get something like this. Read this for me. Somebody we have not yet heard from today, just to mix things up. No tricks yet. You've seen the call and the data. Anyone?
I think you're seeing numbers that or that is stimulating.
Which should be the case, right? We should be able to reconstruct the shape of the relationship that we artificially constructed in the first place. It should not be surprising that we can recover the thing we analytically modeled in the first place, right? So you get the same slope we had before, 0.08 more defects found for every additional minute of review time. There's some, intercept value here, right? Some baseline level of defects found, and a model that fits pretty well. Okay. So this should look like the thing from before, right? Which we artificially created. Okay, no surprises? I feel like you don't trust me anymore. I don't know what's happening. Like this extreme skepticism. I tell you when I trick you, right? So, yeah. Okay. This is just the plot of that relationship and the raw data. Okay. So this is the relationship we modeled. Okay, so now if we these numbers don't make any sense. Interesting. Claude is being weird. This is why this needs some iteration. Okay, so now let's say we do this. Like I mentioned earlier, this was Shrey's example from last time, is a number of developers, participants, each performs a number of code reviews. Okay? There's a fundamental assumption that we're breaking if we're modeling the data this way. The fundamental assumption is that these observations are independent of each other. Okay, that's the fundamental assumption for this to be legal, right? The reason why we're breaking it is because we know that it's the same participants being observed on multiple of these code review tasks. So, if you're really good at code review, you're probably going to find more bugs, regardless of, the tool you're using or how much time you spend, than if you're really bad at code review, right? There's an intrinsic individual level factor here that probably explains a lot of the variation in outcomes.
Won't the control variable account for that?
But we have not introduced any control variable.
Oh, I see.
We just modeled a pool of observations as if they're all independent, right? So this will happen in the research you do probably a lot. There will be some kind of hierarchy or nesting in your data, probably almost always. Be it individuals observed multiple times, be it, I don't know, things that are part of some higher level structure, right? Like all these sources of grouping or hierarchy in the data that could introduce non-independence, right? You can reasonably expect that if you're very experienced as an individual, you'll do better at whatever tasks. If you're a very experienced programmer, you'll do better at programming tasks than if you're not. If you're at CMU compared to at some other school, you can reasonably expect that your, I don't know, GPA is going to be higher or your job market outcomes are going to be better or whatever else, right? Because of this, school that introduces this clustering dimension here. Like CMU students are more homogeneous and similar to each other than a CMU student is to some random other school student. Okay, etc. So there'll be lots of sources of nesting in your data that you have to deal with somehow. And you cannot just pool all of these observations, which is kind of the baseline assumption for this standard way of modeling. Right, so here's some more examples, right? Multiple commits from the same developer, multiple releases from the same project, multiple tasks performed by the same participant, multiple files in the same module. All kinds of sources of hierarchy or nesting or clustering that could introduce non-independence. Okay, so if you have non-independence, you have to do something with this explicitly. You have to deal with this because otherwise the original, pool-based model is illegal. You go to jail, right? You're modeling jail, right? So now how? Okay, so here's a more realistic scenario: 8 developers, each doing 8 things. So 8 times 8, 64 observations, but they are not independent. Each developer has a personal baseline thoroughness. We are modeling this, so developer intercepts, we're modeling this as a normal distribution. We're saying the mean is 0, standard deviation of 1, just as an example. This is artificial data. Okay? And then we're simulating how across different reviews, people find, so everybody finds 2 bugs by default when they're reviewing. And then there's some developer specific intercept. People that are more experienced code reviewers find more defects. People that are less experienced code reviewers find fewer defects. Okay. Then there's a linear relationship with review time like we've seen before with the same slope. And then there's some error, mean 0, standard deviation 1, normally distributed. This is simulated artificial data, right? But this is the kind of data that you could get out of an experiment or something like this. Okay? So this looks something like this. So it's roughly the same relationship for all your participants, meaning it's the same slope roughly. There's a bit of noise here because the samples are very small. Okay. But it's roughly the same shape for all your participants. But by construction, as we've defined this, as we've simulated this, the intercept varies between these. So Shrey, what was your example last time?
This is weight loss,
Weight loss.
Yeah.
As a function of some diet?
number of weeks.
Okay, yeah.
That is one.
So it was very similar idea there. Okay, I forgot what it was, so I sort of invented a new one. Or Claude did rather. Okay, so this is what the data looks like. So now you can pool this like before, right? So forget about this nesting, right? Assume you didn't know about this or you didn't care about this. What if you just pooled all of these observations? 8 developers, 8 observations each, 64 total. What if you just pool them? Okay, if you pool them, you have defects found as a function of review time with a simple linear model. Okay, with me? Which gives you about 0.05 slope for review time. So that's pretty close to the one we artificially generated. That was 0.06. You have some standard errors here. Okay, keep an eye on the magnitude of these. Will become relevant in a minute. And otherwise, you have a model that fits pretty poorly.
We initialize slope to be the same across all in the simulation mode.
Yes. But there's some random noise. And because we have so few observations, that random noise makes them be not exactly parallel. They're kind of the same. Look at the plots here. They're kind of the same, but they're not perfectly parallel just because there's a high noise to observation ratio. But I think they're close. They're reasonable. Okay, so right. So this, as I mentioned before, is illegal. You go to modeling jail, right? Because we know that these are not independent observations. You can't just pull them. So what happens is the standard errors are wrong because you're not accounting for this hierarchy or nesting or clustering that's present in the data. Your levels of statistical significance, meaning your p-values, are overly confident, probably, because you assume that you have 64 independent observations that you can estimate this over. But in fact, you have just 8, because you have, 8 people, 8 observations each. And you're not separating kind of what's intrinsic developer level variance from what's extrinsic, just noise. Right. So how do we fix this? This lands you in modeling jail. How do you get out of modeling jail? There's 2 ways.
Understand which variable is higher and then and use that one.
Yeah, so we know by construction that it is the participants, the developers, right? Developers create this hierarchy. We observe each developer 8 times as part of our study. We know what causes the structure, the nesting, the clustering. What do we do with that information?
Do a separate fitting for each developer.
Why not? Why not? Right? Why not do that? Does this make sense? It's like, why not? So, I mean, by construction, we have a separate intercept for every developer. That's how we built the simulation in the first place. So why not model a separate intercept for every developer? Why not do that? Not a trick. I'll tell you when I trick you. This is not a trick. Right? Super reasonable solution here. Which means what exactly? What do I do? How do I change the model? I add something to it, or
Yeah. Yeah, the random effect.
no such thing, no random effects.
Change the.
I mean, you can run an indicator variable or something like that to annotate which observation is for which, but otherwise you just do 8 different fittings with 8 different models.
No. So no random effect. We've not used that word yet, right? We're talking about explicitly modeling separately each developer intercept, but jointly, not in separate models, all in the same model. Okay, so we'll come back to mixed effects as a second solution for this. But the first solution, the most straightforward solution, is to include what in the model? What else?
A new variable.
Say again?
A new variable.
What is it? A new variable. Yes. What is it?
The development.
Yes. Right. A categorical variable that tells me which developer it is. Literally, right? Which I have in the data, right? I have a column in my data that tells me which participant produced which observations. So I know if it's, participant 1 or 2 or 8, right? So I include a categorical variable in the model for the participant, right? I write something like, what is it? Defects is participant plus review time or something. Is that it? Right? That's my specification. This is a categorical variable, the flag, that tells me if it's participant 1, 2, 3, 4, or 8. Right? This is the thing that I had before. So I estimate these regression coefficients. That means, it's like it would be, what does that mean? We talked about categorical variables a couple of meetings ago, a couple of times. So there's 8 of these, right? What actually happens? What gets estimated?
Guessing this will be the intercepts.
Yes, for all 8. So how many of these coefficients do I get in my model summary?
Eight.
A, B, C, D, E, F, G, H. Oops. What just happened?
Well, one of them's gonna have an intercept of 0.
One of them just has it 1. This is respective to that.
Say again.
One of them, like their A is basically the estimate of that it would be 1.
I don't know if I agree with either of you. Is there a third option? We talked about this before when we talked about gender or something else. What did we talk about before? We had more of these. We talked about how R is weird in how it chooses alphabetically what?
So developer A this line, we do not have them.
So by default, right, the default behavior for categorical variables is that the level of a categorical variable, meaning the value of a categorical variable that is alphabetically the smallest, in this case, developer A, by default, that's the behavior. That is chosen as the baseline.
So that is 1.
That is 1.
That's zero.
That's
Yeah, that's zero, that's zero,
both.
because that doesn't add to the equation.
That true? That seems like a trick question. I'm not sure if that's true. I need to think more about this. I'm not sure if that's true.
But then, what else would the default behavior be?
So the point is, we can only ever estimate coefficients for n minus one of these. There are n levels. We can only estimate n minus one of these because the last one, or the first one, or one of them, is always fully determined by knowing the values of the other ones. So the last one cannot be estimated.
So then can we just add like another developer? Post on.
So here, the thinking is compared to developer A, which is chosen arbitrarily as the baseline. Developer B, for example, finds 0.9 more bugs per minute of review or something.
Sure. But then we don't really need to reach the developer.
Developer A,
Like,
developer A is the estimated coefficients are always of the delta, just like 1 unit increase in that variable for numerical variables gives you this much the beta amount change in the response. It's always about the change. It's like you need a reference point. 1 unit increase for a categorical variable doesn't make sense by itself.
yeah.
So the difference from A to B, that's the unit increase, is 0.9 defects. Whatever A is, I guess. So A is,
Maybe
say again,
A would be the row just about develop B, right? Yeah.
would be the overall intercept, right? Yeah. That makes sense. Yes, A would be the overall intercept because all the other ones would be zero in that interpretation. So that makes sense. Yeah. But all of these other ones are relative to A. This is how much either one of these does better or worse.
A would not be the intercept, it would be y minus intercept, right? Y is equal to A plus 0 times all of these intercepts.
Y is equal to the intercept 0.66.
Plus 0 on,
When developer equals A, that means all of the other ones are 0. Okay, and review time is 0. Baseline value by default.
no, review time is not 0. It's it would be y is equal to 0.66 plus 0.06 times review time.
Yes.
This is the equation for what happens when you are developing.
Correct. That is correct. Yes. Very good. Yeah.
What does the negative value then mean for a developer age?
Say again.
What does the negative value mean for developer age?
Yeah. So remember the way we created this. The way we created this is so that the mean is 0 and the standard deviation is 2.5. So that means some of them will be above 0 and some of them will be below 0. It's just how it does, I know, the interpretation doesn't make sense. So this is Claude being Claude here. You can imagine you, I don't know, scaled these or something. They should have all been positive. It can be negative in the real world, I guess. That doesn't make sense. But it's just an artifact of the distribution that was used to create these. So here it means that compared to A, H finds 2 fewer defects at the starting point. And then with more review, they evolve at the same rate. Right? Because the coefficient, the slope of the review time thing is shared between both of them. But it does not vary with developer. The slope is for everyone the same.
So technically, developer B finds 0.9 more bugs than developer A.
Correct.
It's not 0.9 times.
No. 0.9 absolute more bugs.
At any given.
But before they spend any, yes, they start before they spend any review time, I guess at any
Even
point, because they're
throughout,
parallel.
exactly,
Yeah,
yeah.
yeah. Yes, correct. They remain parallel, so the difference is the same. Yeah. Yes, developer B always finds 0.9 more bugs than developer A at any level of or amount of review time spent. Correct. That's the whole point, right? Because we hold constant or fixed review time. We don't care what the value is. We reason about the effect of the other thing. Right? That's correct.
But even if all of them had a different slope, and you would have done this exercise, you would have only gotten one slope of review time.
This model, as specified, can only produce one slope for review time. The specification is what determines the outcome.
But maybe they don't have the same slope.
That's right. So you can model this separately.
Then you'd have to do a separate 8 separate ones. There's no way to do it combined here.
Let's come back to this in a minute, because I don't want to miss the second solution to this. So hold your thought. Does this make sense? This is called fixed effects regression, right? You just add. So the things that create clustering or nesting, you add fixed effects terms, you add variables for them in your regression. I think the economists love this approach for some reason. Maybe I'm wrong, but there's some community of science that really loves fixed effects regression, and they do this for everything. And it's, it's a great solution, except for a few things that are wrong with it. One thing that is wrong with it is that it uses a lot of the degrees of freedom, the information that's available, just to estimate these individual level coefficients that you probably don't care about, right? Because here, your research question is probably about the effects of, review time, not so much about individual differences between developers, between participants, right? So you're essentially burning a lot of information in your data to estimate these coefficients that you don't actually care about. So this is often one big problem with this approach. Yeah, Marco.
So what do you say burning then? It's not like we can't reuse the data to get our other values, right?
Yeah, so right. But so if you have 50 developers, you need to estimate 49 of these coefficients. Okay. So if 50 developers that do 4 code reviews each gives you 200 observations. Okay. So your information space is 200 observations. You're wasting or using a quarter of all that information that you have available just to estimate these individual level coefficients that you don't actually care about. And only the rest remains to estimate the things you do care about. That's kind of the thinking here. If you have a lot of these possible values of the groups, you're using up a lot of information to estimate these coefficients that you don't actually care about. Because you don't care about the absolute values of these things.
Yeah, that makes sense. I'm just wondering why you can't like take it and then plug it back into like, oh, here's developer A, right? And based on this magic that I did in the previous step, I have this intercept, right? That I'm expecting to offset their behavior for this developer. And based on this intercept, now I can see what the slope is actually supposed to look like.
Say this again.
So you had there's like the image for that one. So you go through and you get all the intercepts, like let's say it's everything in comparison to developer A. It's like, oh, developer B versus developer A, developer C versus developer A, so on and so forth. You have the like the changing intercepts for each of them. So then why can't you just use that and apply it to each of the different I think okay, I must be getting lost or something. I just don't understand why you can't like use that information in the future, like and continue doing your analysis. Like,
Let me think more about how to answer this. I'll come back to you maybe next time.
does it make sense what I'm asking?
Not exactly just yet, but I want to touch on the second point before I lose you all in 5 minutes. So let me punt this for now and revisit. So I mean I the point is, I think that the more information you have, the more confident you can be in the estimated coefficients for all of these things, right? So the amount of information is in the input data is fixed, right? It's what it is. It's however many samples you have and how large it's however many samples you have. So the amount of information is fixed. So now you could choose how you use that information. If you use it to estimate a lot of these individual level coefficients that you probably don't care about, because the budget of information is fixed, you have spent a lot of it on something you don't care about. So the remainder is what you spend on the thing you do care about. So that's kind of the argument, but I don't have a better explanation for kind of why your suggestion doesn't make sense or how that compares. So let me think more about this.
I understand
Okay, so this is roughly why this is not a good idea, even though I think it's perfectly legal. You do not go to modeling jail if you do this. It's absolutely perfectly good solution for this problem. The second solution for this problem is the one that Shrey talked about last time. So here, instead of estimating the individual coefficients for all but one of these developers that we don't care about, what if we just estimate the variance in these intercepts? So this was Shrey's point from before, right? So we are assuming that each of these developer intercepts is drawn from a normal distribution. We don't know what the variance of that distribution is. So we're trying to estimate that one parameter instead of n-1 individual coefficients. So I don't care about the individual values of these intercepts, but I do want to estimate the variance of that normal distribution from which these intercepts are drawn. Hence the term random effects here, right? Which is what Shrey mentioned before. So what that would look like is something like this. So I'm saying, look, it's still defects as a function of review time, but there's a random intercept. The one here means intercept. There's a random intercept for each developer. That's the syntax. So I'm saying I don't want a individual coefficient for each of these developers, but rather I want to estimate literally the variance of this normal distribution from which these intercepts were presumably drawn. Okay, so that's one parameter, not 50.
And because it's a random variable, it's called random.
Yes, yes. Right, so I'm assuming that all these developer intercepts, that's a modeling assumption. I'm assuming that they're all drawn from this distribution that's normal shaped. Okay. So this was your point, I think, last time with the weight loss. So here, what happens is I get, so part of the summary of this model is all the stuff from before. So the fixed effects are much like before. I actually get a better estimate of the slope. And look at how tight these standard errors are. Remember what they were before? Did you pay attention? So look at the 0.005. Okay. Look at the ones before. Review time for review time for fixed effects model, similarly tight standard errors, same slope. I told you this is perfectly legal. You don't go to modeling jail if you do this. But if you look at the naive one from before, the estimate is a bit off, but the standard errors are orders of magnitude higher here.
So saving the degree of freedom, what benefit did we get? We got the same estimate in the final two solutions.
My point with this is I am much less confident in this estimate with the naive model than I am with either one of the legal models. And now your question?
But is the second legal model better than the first one? Because that is consuming less degree of freedom, right?
Yes.
But
That's,
still the estimates are the same, so I don't care.
but okay.
No, as in like technically speaking, we had more information about the data in the second model, right? We knew that, oh, these intercepts are part of normal distribution, which is what saved the degree of freedom. So technically, when you have richer input, you should have gotten richer output.
On real data, you will get
Like,
slightly different output. Yeah.
it
Or
would be tighter than this should be tighter than the previous one. That's it.
yes. So you have more information available to more precisely estimate the other things in your model. So you should get better more precise estimates of the other things in your model with the second model, with the mixed effect. So it's called mixed effects because it has a fixed effect, which is all the things from before, and this random effect, which is this random intercept for developer. Okay, so now let me just finish reading this output. So the fixed effects part is interpreted as before, right? So you have a slope estimate and you have standard errors and so on. You can get p-values for these if you call a different function. And then there's a random effects part of the summary. So this tells you that so the variance here, this is what gets estimated, right? That's the variance in the distribution of these developer level intercepts that I randomly draw them from. And it turns out, remember how we created the data in the first place? We said
Mean of zero, standard deviation of 2.5.
mean of zero, standard deviation of 2.5. We said those are the developer level intercepts. Look, I made them here. Okay, so pretty good reverse engineering here. Because look at that, I got exactly the standard deviation back. Okay, but the point is, I now use one, degree of freedom, unit of information, to estimate this parameter for the model instead of 50 or however many, like one for each level. Okay. The other thing you could look at here is how much of this variance is attributable to within developer variation versus residual stuff. So you could compute, for example, the sum of these two things. So do I have one here? Yeah. So if you compute the sum of these two things, right? So like 6.2 plus about 1, okay? So the developer level variance is about 86% of all of this variance here. So that's a lot, right? All of this you're ignoring with the naive approach. Right? So almost all of the variance in our data, in our observations, is due to it's due to between developer differences here. That make sense?
And what does the residual value show?
The residual is whatever is left over, whatever I cannot explain. So if you remember how I created this,
The noise that.
it's this thing. Right? So I cannot perfectly recover the things. There's some noise. The residual noise is whatever residual noise is there. Or some other variables that I didn't, model, or, confounding factors or whatever, right? But you can see, on this artificial example, how important this between developer variation is. So pause here for questions. This is really critical. Like, you have to remember or understand this part. It will come back every time you do any kind of modeling. This idea of mixed effects regression will come back not just in linear regression, but in all forms of regression. It's a really useful way of modeling anything. It's a critical life skill that you're learning today. Okay, we'll do one hands-on on Thursday, unless we have some readings. Do we have any readings on Thursday? You have one on Thursday? We'll do a reading and some hands-on stuff on Thursday. So you can practice this yourselves. Maybe think about this in the meantime and come back with questions, or just ask Claude. Claude is better anyway at answering questions. And if you're still confused, ask me. Chances are I'm worse than Claude, but you could try. All right, thanks.